Okay, welcome to the fourth example. In chapter 3, the question reads, the short cylindrical block of 2014 T6 aluminum having an original diameter of 12 millimeters and a length of 37.5 millimeters is placed in the smooth jaws of a vise and squeezed until the axial load applied is 4 kilonewtons. Determine A, the decrease in its length, and B, its new diameter. Okay, so we can start off with the mechanical properties of this given material. And in this case, it is 2014 T6 aluminum. T6 aluminum. And in this case, we're going to use two mechanical properties, namely, firstly, the elastic modulus. And in this case, it has a value of 73.1 gigapascals, and Poisson's ratio. And Poisson's ratio, in this case, or for this material, has a value of 0.33. And what does Poisson's ratio describe? Well, it describes the ratio of, or it relates the lateral strain in a material to the longitudinal, I don't know if that's a word, but we're going to go with it. The longitudinal strain. And what does that mean, like, physically, in, like, this diagram, for example? Well, if this is my longitudinal axis and this is my lateral axis, if I apply a force longitudinally, like, how do these two relate to each other? If I apply these forces, these 4 kilonewton forces longitudinally, what's going to happen in the lateral direction? Well, it's going to kind of expand, right? And then again, for example, if I were to elongate instead of compress, it would kind of compress the diameter of this material in the lateral axis. And a much more simpler example, physical example you can think of is if you have like a marshmallow, right? And let's say this is your lateral axis and this is your longitudinal axis. So longitudinal, lateral. What's going to happen if I pull this marshmallow in this direction? Well, the diameter is going to get smaller, right? And then again, if I compress this same marshmallow, then my diameter is going to get bigger, right? So basically relates, it's a value that relates the lateral strain or the lateral deformation to the longitudinal strain or deformation. Okay, so we can write down the other givens. We're given the initial diameter, so D naught is equal to 12 millimeters. We're given the original length. L naught is equal to 37.5 millimeters, and we're given the force, or the axial force in the longitudinal direction, to be 4 kilonewtons. Okay, we can move on to unknowns. This question, fairly simple. It wants us to find the decrease in length because it's being compressed, right? So we're going to have a decrease in length. So once we eventually do find our delta L, we know that it's going to be negative. And so we want to find delta L, and we also want to find our new diameter because, as we said, once we compress this aluminum bar, what's going to happen to our diameter? What's going to happen if we compress this marshmallow? Well, it's going to kind of squish outwards. Not as much as the marshmallow, but this aluminum is kind of going to have a very small deformation to its diameter. It's going to increase, right? Okay. So we want to find D1. Okay. So firstly, we can start off with finding delta L. Find the deformation in the aluminum block. If we write down delta L, we branch off. We have the longitudinal strain, or delta L is equal to the longitudinal strain multiplied by the original length. We know the original length to be 37.5 millimeters. We know that the longitudinal strain is equal to the stress in the longitudinal axis divided by the elastic modulus. Do I know the elastic modulus? Yes, I do. It is 73.1 times 10 to the power of 3 megapascals. Do I know stress? Well, stress in this longitudinal direction is equal to the force, in this case 4 kilonewtons, right? The axial force applied, divided by the area. And the area is simply, again, it's like a circle area, or spherical, no, not spherical, circular, that's the word. Circular area, it's going to be pi over 4, the original diameter squared, right? So D naught squared, this is going to end up 4,000 newtons divided by pi over 4, 12 millimeters squared. You're going to end up getting a value of 35.368 368 megapascals. Perfect stuff. If you evaluate for your, the reason I'm evaluating for longitudinal strain is I know that I'm going to use it later. So yeah, so if you do this calculation, you do 35.368 megapascals divided by 73.1 times 10 to the power of 3 megapascals. You're going to get that your strain in the longitudinal direction is going to equal 0.123 4 or 000 483827 millimeters per millimeter. But there's one thing we need to add to this thing, or to this strain. I know that this strain is going to be negative, right? Because this force is compression. And if I were to evaluate this delta L is equal to longitudinal strain. Let's just say I didn't know that. 0.000483827 millimeters per millimeter multiplied by the original length, 37.5 millimeters. Didn't I say before that this value is going to be negative because it's in compression? If I do this calculation, I'm going to get a positive value. So what has to be negative? This original length cannot be negative. That means my longitudinal strain has to be negative, right? And it makes sense as well because I'm going to have a negative strain. It's going to decrease in length. So that is where that negative comes from. So I'm going to add the negative there, add it right here. And I'm going to get a delta L, a decrease in length of negative 0.0181435 millimeters. And you can add at the end if you didn't realize that. But this is how much your bar is going to decrease in length by. Okay, step 2. We want to find, let's make this smaller. We want to find the new diameter, right? And with this, we're going to use Poisson's ratio. Because, as you know, Poisson's ratio, it compares the lateral strain and the longitudinal strain. We have the longitudinal strain. We have Poisson's ratio. We don't know the lateral strain. But what is the lateral strain equal to? Well, the lateral strain is just equal to, remember, strain as a value is equal to delta over original, right? Original, right? So if I know that the longitudinal strain is equal to delta L over L naught, right? And that makes sense. Then, and that's in this direction, what's the lateral strain equal to? Well, in that case, the lateral strain will just equal, again, not delta L over L naught, but it'll be delta in the diameter, right? Delta D over D naught, right? Because it's just the opposite direction, or the perpendicular direction, right? So with that, we can find the new diameter, D1. So that'll be our step 4. Find new diameter, D1. Okay, so we can branch off. I know that my new diameter, D1, is going to equal my original diameter plus the change in my diameter, right? So it's D naught plus delta D, right? Do I know D naught? Well, yeah, I do. It was given in the question, 12 millimeters. Do I know delta D? Well, not yet, but I can find it. But let's just say that we know what this is. This is equal to 12 millimeters. But I don't know this one yet. I know that delta D, from this equation that we just explained, that the lateral strain is equal to delta D over D naught, right? The change in diameter over the original diameter. So I can replace that, right? So I can replace it with the lateral strain multiplied by the original diameter. Okay, again, do I know the original diameter? Yes, I do. It's 12 millimeters. Do I know the lateral strain? Well, not yet, but I can easily find it with what? Well, I know the Poisson's ratio is equal, it relates the lateral strain with the longitudinal strain, right? And I know Poisson's ratio, it has a value 0.33, it was given value, given mechanical property, and I calculated the longitudinal strain up here, right? So if I plug all that in, I can say that my lateral strain is equal to Poisson's ratio negative Poisson's ratio multiplied by my longitudinal strain, right? If I plug in my numbers here, I will get that my lateral strain is equal to negative Poisson's ratio 0.33 multiplied by my longitudinal strain, so negative 0.00048387 millimeters per millimeters, and you can see that the negatives beautifully cancel out here, and you can understand now why there's a negative in this formula, right? Latitude over longitude basically says if I compress it this way, then if I compress it this way, then the forces this way, the change this way is going to be opposite, right? Basically inverse relation. But yeah, so if I complete this calculation, I'm going to get my lateral strain to have a magnitude of 0.0001596629 millimeters per millimeter. Right, keep as many digits as you can because it's a small number, but if you use a calculator, you don't have to really worry about that. Now what do? Well, I plug it back into my original equation, find delta D. Bring this guy down. Delta D is equal to my lateral strain. I don't want to write, actually, fine, I will. My lateral strain, 0.0001596629 millimeters per millimeter multiplied by my original diameter, 12 millimeters. Once you do this calculation, you're going to get that your change in diameter is equal to 0.001915959492 millimeters. And finally, to find my new diameter, I'm just going to add this change in diameter to my original diameter, right? So if I bring this one to this side, I know that my new diameter is simply going to equal my original diameter, 12 millimeters, plus the change in diameter due to the longitudinal axial force. .492 millimeters. And then finally, I'm going to do this calculation to find my new diameter, 12.000191, and I'll stop there, 6 millimeters. And that is the new diameter of your aluminum bar. So these are your answers: your decrease in length longitudinally, and your increase in diameter, or your new diameter in the lateral direction.